Okay, welcome. So today I'm gonna finish up the last topic on thermodynamics. It's gonna be gas laws, and then I'm gonna briefly cover the laws of thermodynamics, just kind of as a little finisher there. This lecture should not be too awfully long. Okay, so first thing, share the notes. All right. Okay. So again, lecture 31, gas laws and laws of thermodynamics. We'll start off with the hello. Start off with the gas laws. I don't know why this is happening. Okay, that's no big deal. Um, yeah. Okay. So starting off with the gas laws. Now before I get into the different gas laws, I just briefly want to indicate kind of what they are. Basically, when people were first looking into the laws of thermodynamics, one of the things that and this crosses over with chemistry. But one of the things they did is they wanted to see it was well understood that changing something like the pressure would increase the temperature, or changing the temperature could change the pressure or the volume or whatever. People wanted to have explicit relationships here, and that's basically what the gas laws were. So there are four big gas laws that are going to apply that relate the four major quantities, and then these are ultimately synthesized into the ideal gas law. So if you've seen the ideal gas law before, that's what that is. Now, before I go too much further in this, I just do want to make a point that in these gas laws, any of them, you must use uh absolute absolute pressure and temperature. Okay. Now, what this means is it means that you have to have P absolute. So P absolute, as a reminder, that's your P gauge plus P atmospheric. Now, P atmospheric is approximately 101 kilopascals. Like that will be a sufficient number to use, sufficient number of significant figures. And then you also want your temperature in Kelvin. Now, sometimes you'll be given gauge, sometimes you'll be given absolute, but you will almost always be given temperatures in Celsius. You have to convert those to Kelvin in order for any of these gas laws to work. Okay. So that's a non-negotiable. That's a non-negotiable thing about how this goes. But in any event, let's jump into those gas laws. First one is Boyle's law. Now, Boyle's law, basically what he did is he wanted to just investigate the relationship between P and V. So what he did is he held the temperature constant. Now, another thing that's important to hold constant is the amount of gas, and N, where N is the number of molecules constant. There's another way to measure the amount of gas. We'll talk about that when we get to the ideal gas law, but it's in moles. But number of molecules, number of moles, they're just two different ways of representing the same quantity. Basically, what you don't want to be doing is introducing extra matter into the situation. Figuring out, how many molecules equal, figuring out how to measure that accurately is actually somewhat difficult. So Avogadro's law is the last one we'll cover, but in any event, we'll get to that. We'll get to that in a minute. But the point is, in order to hold T constant, basically what you want to do is you want to operate this experiment in a temperature bath such that it can always get back to that temperature, whatever you're holding it as constant. And then holding the number of molecules constant is pretty easy. You just make sure that no gas can get in or out. You need a pretty good seal, but as long as you have that, it's good. Now, basically what Boyle found is that at any point, if you take the product of the pressure and the volume, that's equal to the product of the pressure and the volume at any other point. So the point is that pressure and volume can both change in this situation. So you might do this by having like a free moving piston. Um, And the idea is that as long as you hold it at a constant temperature, you don't let any gas in or out, you set the pressure to something by applying a known force to that piston. In that case, your pressure would just be your force divided by the area of your piston. And then you can see how the volume changes. Okay. So basically that's what he's seeing with Boyle's law. Now the next one was Charles's law. Charles' law. And the relationship that the scientist Charles was looking for here is he was looking for a relationship between V and T. Now, in order to do this, he had to hold P constant and N constant. So the N is just, again, the number of molecules. And the holding a pressure constant, you probably still want a cylinder that was free to move, but you'd basically let it adjust manually on its own, and it would kind of adjust to atmospheric temperatures. Now it'd have to be pretty well lubricated, like it would need to be really free to move and free to move under sort of any circumstances. But the point is that you should be able to see that relationship. Okay. And what he found was that if you take the fraction of the temperature and the volume, at one point, that is equal to the fraction of the temperature and the volume at some other point. So this is what Charles' law stated. Then we have Gay-Lussac's law. Lussac law. The relationship he's looking for, this experiment was looking for, was between pressure and temperature. So he's going to hold volume constant. So the V will be constant in this case. And again, so will N. So to hold volume constant is not that bad. You need a rigid container. Now you are probably, if your container is rigid, you can't adjust the pressure just by pushing down on a cylinder. So you're probably going to need something to measure the pressure. So you want this connected to a manometer or something like that, or some sort of pressure gauge. I would imagine that in this experiment, manometer was used. I said manometer. I think it's manometer. In any event, he found a very similar relationship to the relationship with volume, and that is if you take the fraction of the two at any point, any pressure and temperature, go to another pressure and temperature, you'll get that same fraction. Now, lastly, we have Avogadro's law. And what Avogadro is doing is he's looking for the relationship that is apparent here is between the number and the volume. Okay, so you may have like if you took a chemistry class, you kind of assumed this, that I think you assumed that 1 mole is equal to 22.4 liters. I think that's what it is. I don't really remember. It's been a while since chemistry. But in any event, this was something Avogadro had to discover. And getting a fix on how to, keep a set, either measure a number of molecules or keep a, or add a set number of molecules was somewhat difficult. Now, to do this, he held P and T constant. So again, with the pressure, hold the pressure constant. You just want a cylinder that was free to change its shape, but constrained by the atmospheric pressure. And then temperature, you get a hold constant just by keeping it in a heat bath. Now, ultimately, what Avogadro's law showed is that if you take, again, the fraction, N1 over V1 is equal to N2 over V2. So basically the idea is that if you know the number of molecules at one point, you divide by the volume, that ratio is gonna hold true no matter how many molecules you add, so long as your pressure and temperature are constant. Point is that all four of these quantities are interrelated, so there needs to be a final law to do that, and the law that does that is the ideal gas law. So we have our ideal gas law, sometimes called the IGL. And what you have here is you have two different versions. The physics version looks like this, is that you have PV equals N, and then you have some constant KB times T. Now, KB is called Boltzmann's constant. I don't remember what the name of the constant is for the chemistry one. I think there's two in Boltzmann. But the Boltzmann constant and KB, it is equal to 1.38 times 10 to the negative 23rd. And the units end up being joules per Kelvin. Molecules don't have a unit. That's just a counted number. So there's no unit to cancel out with the N. The Kelvin is to cancel out with the temperature. And you can check that if you multiply pascals, which is newtons per meter squared, times volume, which would be in meters cubed, you would get Newton meters, which would be just be a joule. So that's the units of Boltzmann's constant, joules per Kelvin. Okay, so that would be the physics version. Now, the thing about it is that you're dealing in normal situations, you're dealing with huge numbers of molecules. Okay, on the order of 10 to the 23rd molecules. So in chemistry, they ended up using something that was measuring effectively the same thing, but just in larger groups. And that group was called a mole. So the chemistry version, basically what they said is they have this conversion. They have 1 mole of material is equal to 6.02 times 10 to the 23rd molecules. Okay. So that is what 1 mole is equal to. And then they rewrite the ideal gas law. The IGL looks like this in chemistry because they want it in moles instead of molecules. So it's PV. And then this number, it becomes a lowercase n, and instead of K, we have an R. So it's PV equals nRT. And then N is the number of moles. And R, I think, is just called the ideal gas constant, as I recall, but it is 8.31 joules per mole Kelvin. Okay, so that is what that's what's going on with the ideal gas law there. Now, what I would like to do is take a that's not good. Oh, that's what happens when you click on the keyboard. So I want to grab a couple of example problems just to go over them. All right, so what we have here, it's a little bigger. Oh, too big. Okay, what we have here is it says, suppose your bicycle tire is fully inflated with an absolute pressure of 7.00 times 10 to the 5th pascals, gauge pressure. So they're giving you an absolute pressure, so that's fine. This is what we want to use. They're indicating the gauge pressure, but wouldn't bother with that. Because if we're going to use the gas laws, we don't need this. Now the temperature is at 18, and then they want the pressure after the temperature changes. Now, if you're dealing with changes in a system, odds are, not necessarily, but it's a good chance you want to use one of the specialized gas laws, not the ideal gas law. The reason is if you try to use the ideal gas law, you end up having 2 unknowns. So I just want to show you what that means. So what they've given you one pressure is 7.00 times 10 to the 5th PA. And then they've given you your temperature is equal to 18. Now, careful with this. It's not equal to 18. It's equal to 18 plus 273, which would be 291. Okay, so you got to put that in Kelvin. Now they also give you a second temperature. T2 is 35 plus 273, which would be 308 Kelvin. Okay, so the idea here is even though, we've close to doubled the Celsius temperature, in an absolute scale, we really haven't changed it by that much. And the differences in pressure are actually going to reflect that. It's not going to be a doubling of pressure. Or whatever. It's the pressure is going to reflect that your temperature change is not as huge as it first seems on the absolute scale. Okay, so that's one thing. Now, what we're after is P2. Now, if formulating it this way, you might realize that what you want to use is the Gay-Lussac law. However, I'm gonna show it to you with the IGL and just show you the problem. So if we wanted to do this, we would have P1. Oh, also it says no appreciable leaks or changes in volume. So this is saying that V1 equals V2. And this is saying that N1 equals N2. So you're not losing any of the air molecules. So what we have is we would have P1, wait, how I want to do it. P1, V1, and I'll erase the 1 because, again, the V is just constant. So, and then that's equal to N, which is also constant, KB T1. Well, the issue is we don't know, well, we do know KB, but we don't know either V or N. So given that, like, what are we going to do? Well, if you were going to do it with the ideal gas law, basically what you'd want to do is you'd want to, since you do know that N and V are constant, you can basically solve for some ratio and then plug it into the other equation. So you also know that P2V should be equal to N KB T2. Okay. Now the idea here is now you have two unknowns. Well, yeah, you really have three unknowns, but you don't need to find N and V. You can basically find a ratio and eliminate it. So if we were to solve to kind of manipulate this first equation, I'm going to do that real quickly. What I would do is I would say, okay, P1 equals N over V, not N over N, but N over V. And then I'm going to just put the KB in there because that's a constant. And we know that that was a constant. Okay. And then T1. Well, the idea here is we could do the exact same thing over here. We could have P2 equals N over V. I keep writing N, I don't know why. V KB T2. And the idea here is that these two constants are the same. So if we solve for it, we could just set them equal to one another. Now, when we do that, we have P1 over T1 equals N KB over V equals P2 over T2. Well, notice that we don't even need this. And this is just the GLs. This is just the Gay-Lussac law. Okay. So that's basically what we would jump to eventually. And when you want to solve for P2, you just get up that P2 is equal to T2 over T1 times P1. And then that's just plugging in the numbers, just making sure you've got your temperatures right. So it's 308 over 291 times 7 times 10 to the 5th. Okay. Now notice if you tried to do that in Celsius, you would get that ratio would be completely wrong. Okay. So that would not work. And so you got to make sure you're putting this into Kelvin. Okay. It's very important. All right. I want to do one that also just requires the IGL, the ideal gas law. So this next one is a little different in that what we have here is we don't have it going from one state to another. We're trying to calculate some unknown in the ideal gas law, which is the N. So we're looking for the N. Okay. And they do tell us that, 1 cubic meter. So they give us volume is 1 meter cubed. They give us standard temperature and pressure. Now it's important to know what these are. They do say 0 Celsius in atmospheric pressure. So that's P atmospheric. Now, as a reminder, that's approximately 101 kPa, which would be 101,000 PA and SI. And we want to put everything in SI. And then 0 Celsius is going to be 273 Kelvin. We gotta convert to Kelvin here. And now basically we also know that KB, that's just a universal constant, 1.38 times 10 to the negative 23rd. We know that that is set up. And so we can basically set our ideal gas law. PV equals N KBT, solving for N equals PV over KBT. And then that's just going to be 101,000 times 1.38 times 10 to the negative 23rd over 270 times 273. Okay. And you're going to get something in the ballpark of 10 to the 26th, I believe. So that's roughly the 10 to the 26th is a rough order of magnitude for, human scales worth of gases. That's roughly how many molecules you're dealing with in that context. Okay, so those are the two examples. I do briefly want to talk about the laws of thermodynamics as well. Now, the laws of thermodynamics, they actually come out of the Industrial Revolution after it. So people have already invented the steam engine. And a lot of these laws come out of studying the principles that the underlying scientific principles that sort of enable the steam engine. Now, they weren't known before this. The steam engine designers, like people like James Watt, were basically tinkerers that figured out ways to make these things work. The science describing them came a bit later. So, but essentially, this is what leads to these laws of thermodynamics. Now, there are four, but they're numbered kind of funny. The first one is the zeroth law, and basically, it's called the zeroth law because they decided it was more fundamental, but they had already defined the laws of thermodynamics, and this is the law of thermal equilibrium. And as a reminder, what equilibrium means, it means that like the physics is settled, that there's that nothing really needs to happen, that things are stable. If it's in non-equilibrium, that's when the physics principles become operative. So static equilibrium is when you had no acceleration. When you had non-equilibrium, that's when you had an acceleration. That's when the kinematics laws came into effect, all sorts of things like that. So thermal equilibrium. This occurs, the thermal equilibrium, and so occurs when two systems. So we'd say these two systems are in thermal equilibrium if they have the same temperature. Okay, so having the same temperature is basically an indication that no real thermodynamics, no interesting thermodynamics is going to happen in these systems. Now, that's not entirely true, but it basically means that no heat will flow, which means that a lot of what we do in thermodynamics is not going to be operative here. They're in thermal equilibrium. All right, now, first law, this is conservation of energy. When it comes to the conservation of energy, basically what we're looking at the thermal energy of a system. And this can basically be changed in two ways in the context of thermodynamics. It can be changed by adding heat or by doing work on the system. Okay. Now, heat can be added in a number of different ways. It can flow spontaneously from a hotter region. You can have locally hot regions within the system generated through chemical reactions or things like that. You can have friction generating heat and flowing into the system. So the idea there is that heat is capturing a lot of phenomena. Work is something that involves changing the shape of a system, changing the shape or size of a system. And that could, positive work would increase the internal energy of a system. Negative work would decrease the internal energy of a system. Something you will see, I'll put this in green, for engineering, is you'll see it written slightly differently. So your internal energy, your thermal energy. A lot of times it's just written as U. I'm trying to remind you that this is in fact the internal thermal energy. It's equal to Q minus W. They do it minus because in engineering context, a lot of times what you want is the work you care about is the work the machine is doing. So you quantify that work as positive work. Now, if a machine does work, it does so at the expense of removing energy from the machine. Okay. So that's the idea. So basically, if you have a minus, it represents work done by the machine, whereas a plus or by the system, whereas a plus represents work done on the system. Okay. So go back to the other color. And then we have the second law. This is the reversibility. This is the law of reversibility. And basically what it says that thermodynamic uh, physics basically has a direction that it goes. And the idea is that heat will flow spontaneously from high T to low T, but not the other way. And this means that even if your energy is conserved, you can't just move heat around to wherever you would prefer it to be. It will spontaneously move in one direction. And if you want to move it in the direction it doesn't want to move, you actually need to do work. And this is one of the things that is interesting about thermodynamics. A lot of it is not about it's about how you can sort of rearrange heat and work and internal energies in order to get something useful out of the system, but you have to obey the second law, and that's basically that things happen only in one direction. Now, the third law, this is the law of entropy. And basically, it says entropy in the universe is increasing. That's the sort of summary version way to put it. Now, some people think of entropy as disorder, and that's correct. That is an accurate way to think about uh, entropy. But it doesn't quite capture all the nuance behind entropy. Basically, what entropy means, it means it's what it's related to is sort of the distribution of energies across different molecules, and so basically, an entropic state is kind of a more likely state, and so the whole idea, like when you combine the second and third laws, the reason why heat flows from high to low temperature is because that is a state of higher entropy. So basically, entropy is sort of a measure of how of sort of it's a quantity we can think of as maximizing when heat is going to flow. So entropy is, like I say, that's a good chunk of a statistical mechanics class in and of itself. Not going to go into that, but it's just worth knowing that that's what entropy is. And you can kind of think of entropy as just disorder. That's fine. Um, so I just wanted to talk about just talk about heat pumps, or sorry, heat engines, and then heat pumps. So a heat engine, basically, this is a thermodynamic device that uses heat flow from high T to low T to generate work. So any engine that basically involves the generation of heat. So like the engine or the motor in an electric car is not an example of a heat engine, but gasoline engines are heat engines. Diesel engines are heat engines. Steam turbines are heat engines. So basically, you're generating a lot of heat, and then you're turning some of that heat into work. That's basically what a heat engine is. Okay. Now another thermodynamic device that comes up in the study of this is a heat pump or refrigerator. And these are doing something similar, but the way they're measured is slightly different. Um, Basically what you're doing here is these use work, let's say uses, because it's two categories of thing. Use work to move heat from low T to high T. Okay. That is fundamentally what a heat pump is doing. Now, the difference between a heat pump and a refrigerator has to do with how you measure the performance, which is, I'm not going to go into that here, but they basically do the same thing. It's just how well they do it. You care about slightly different things, so you're looking at slightly different things. So that's basically what I have to say about heat engines and heat pumps, so on and so forth. So I'm going to go ahead and end the lesson there. Maybe I am. If I can figure out how to stop sharing. Oh. There we are. Okay. So thank you for joining me today, and I will talk to you in the next lecture.